Let me write them down first. So on the left-hand side, we have the acceleration of a fluid particle. U is going to be the velocity, so time derivative of u plus u dot u. This is just a chain rule. And the right-hand side is the total force acting on this particle. So it's minus the pressure gradient, right? And the friction force, which is modeled as some positive number nu, which we call the viscosity coefficient times the Laplacian u. We will be on a d-dimensional torus. That's the simplest setting for the Navier-Stokes. U is divergence free. Again, and I'll talk about various issues related to the regularity. When I say regularity, I mean smoothness. When there is no force, regularity is the same as smoothness of solutions, and uniqueness. Okay, so you'll ask me to make it elementary, so it's I'll try my best. And I'm also supposed to mention the H principle, I guess.
Well, not necessarily.
Anyway, I'll write it down.
Okay. So I even reminded the the people at the workshop that it's the H principle and beyond. So you can just go beyond.
Anyway, I'll go beyond that. At least in the beginning, let me mention it. So we all remember the definition by Yasha, right? So there are two keywords, constraints and constructions, right? Or I'll be more vague, obstructions and constructions. Okay, so to have H principle, ideally I want to identify all the obstructions, and then for that in a complement you can do constructions anywhere you want, right? So now you have to decide what you want to construct. For the uniqueness, it's clear, right? You want to construct different solutions starting with the same initial data. For the regularity, there are a couple of things that you want to do. So first, of course, the first thing you try is to construct smooth solutions. So given initial data, can you construct smooth solutions? And you'll see that there will be obstructions for that. And then if we fail, then maybe you want to start constructing solutions that blow up. And again, there'll be some obstructions for such constructions. Anyway, I'll still try to make some kind of diagram. All right, so this is in the case where obstructions are positive results. And constructions would be counterexamples to positive results. So by positive results, I mean uniqueness, regularity, things like that. And then most well-known positive result of obstruction in this case is the Prodi-Serrin class. So this is a functional class. There have been lots of extensions to wider spaces, but I'll just write it in the simplest setting. So this is the LP, LQ class, LP in time, LQ in space, such that 2 over P plus D over Q is less than or equal to 2. If you stay in this class, then everything is fine. So there is uniqueness, and solutions are automatically smooth. And as I said, there have been lots of extensions that I'm not going to mention. What I will rather do, I will try to tell you what happens outside of this class. So do you have any kind of non-trivial, so these are going to be trivial obstructions. Do we have some non-trivial obstructions for blow up or for non-uniqueness. Again, so now let me go back to the Navier-Stokes equations. So I already wrote. You can see, right? This is the only time I'll use a sideboard. I wrote it in Fourier space. Let me try to explain it very briefly. Camille already showed it to us. The only thing I did here, I integrated in time, and I'll tell you why. So this is a Fourier coefficient on time t. It's equal to the Fourier coefficient at time 0 plus integral. So this is the linear term, right? The Laplacian in Fourier space is just multiplication by the magnitude of k squared. By the way, again, try the divergence-free conditions. It's k dot uk 0. This is the divergence-free condition in Fourier space. And the non-linear term becomes something like this. It's a convolution, right? So in physical space, we have a product. It becomes a convolution. And here, you have a choice because of the divergence-free condition. You can either put here k or h, right? So because say that uk is 0. So when you write it as k dot uk, you basically think about the divergence form of the nonlinear term. Divergence of u times the okay, it's the same thing because of divergence condition. And this is just the projection on the divergence-free vector field, right? So we call it Leray projection. And why did I integrate in time? Because now what we have is the definition of a weak solution. Okay. So for us, what is going to be a weak solution? It's going to be a sequence of Fourier coefficients. What we are going to assume that they are continuous. So each Fourier coefficient is a continuous function. And to make sense of the nonlinear term, what we need to do, what we need to know is that the literal to norm of this sequence is right. So that's going to be the definition of a weak solution. The question is, does they exist? Well, for example, do we get this condition or not? And indeed, if you look at the L2 norm, if you look at the energy, so that's the L2 norm of u squared. By multiplying your equation by u and integrating, or if you like to stay in Fourier space, just multiply with the Fourier coefficient, and in this sum you replace k with h, you'll see that the sign will change, so it disappears. And what's going to the left is have the energy at time 0 minus the total dissipation, so minus nu times the integral of the gradient u of the So if you start with finite energy, the energy cannot increase, right? So then if you fix a Fourier coefficient k, so fix k, you look at the sequence of Fourier coefficients, sorry, you look at the following sequence. So let me do the following. Let me take a summation for h, which are less than some number capital N. This is what we call a Galerkin approximation. It's a finite system of ODEs, right? You can solve it. Now, what happens to each Fourier coefficient? It's uniformly in time. In N continues. Right, so we can just apply the Prodi-Serrin theorem, and it gives you the existence of the subsequence Mj such that U and J uniformly converges to some continuous function U. So again, for each fixed k. And then it's easy to check that this function satisfies this equation. So this is just a simple computation. The nonlinear term is only one which is problematic, but it's just a simple computation. It converges. Weak solutions exist. Globally in time. It was proved by Leray in 1934. Moreover, they satisfy some rather nice properties. So the energy equality, which I wrote, of course, it's equality for Galerkin approximation. It's exact equality. But once you pass to a limit, right, the Arcellas-Colli theorem gives you weak convergence in a sense, right? So each Fourier coefficient converges separately. So norms can drop in general, and you get inequality. But you can do this starting not just 0, but starting from t0. So it's true for any t larger than t0, almost all t0. And such solutions are called Leray-Hopf. So what's so special about Leray-Hopf solutions? They cannot blow up instantaneously. So again, this is one of the results by Leray with strong uniqueness. For example, if you look at the H1 norm, the solution, if H1 is continuous, then the solution is smooth, right? So one can just look at H1 norm or any subcritical norm for that matter. So such picture is not possible for the Hopf solution. It cannot blow up instantaneously. So weak solutions like this might exist, but they would not be again. So for Leray-Hopf solution to blow up, first need to have a blow up from the left, and then and many different things can happen. So such a solution can be potentially Leray-Hopf. Okay. Any questions? So why did I start with a weak formulation in Fourier space? So one of the reasons was to show you that if a blow-up occurs, so each Fourier coefficient is a nice function. It's actually a Lipschitz function. So if blow-up occurs, each Fourier coefficient has no idea, right? I mean, on its whether blow-up already happened or it's about to happen. It's a collective behavior, right, or misbehavior. So in some sense, they're just passing energy to each other, and then if energy somehow manages to escape to the infinite Fourier coefficient, you have a blow-up. Maybe let me start with a simple model. I'll show you some toy models. Okay, so the simplest one is going to be a mechanical system. Right, so let's take some wheels. You can think about Fourier coefficients here. So the energy of each wheel would be represented by a Fourier coefficient, or what's better, think about eddies. So in turbulent flow, the energy moves to smaller and smaller eddies. So big eddies transfer energy to smaller eddies. And now we are going to attach a handle to the first wheel and rotate it so that the angular velocity is always 1. So now what I'm going to do, I'm going to attach a second wheel to the first one. If you change the timing belt recently, you've seen something like this probably, right? So here I'm not going to tell you exactly what's happening here. Think about some kind of clutch mechanism, 2 plates next to each other. So that the second wheel starts rotating as well. And of course, there's always some friction. Energy dissipates to heat. So we might have to rotate the handle a bit, have to apply a bit stronger force. And then we are going to attach another wheel and we'll keep doing this indefinitely. So in physics, this is what we call the forward energy cascade. So we have a heater, right? We have a collection of wheels, and the energy is transferring from the first one to the second, and then from the second one to the third, and etc. So this is the forward energy cascade. So far nothing bad happens, but what you might realize that the work that you have to do is larger than the total heat which is dissipating. Well, it's not clear from, I have to describe the parameters of the system. So let me instead, let me modify it a little bit. So again, let's start from the beginning. Let's start from the first wheel. So now every time I touch a second wheel, I'm going to move the handle. That's the only difference, okay? So I touch the second wheel, I move the handle, and I keep turning it so that the velocity of the first one is still 1. Then I touch the third wheel, I move the handle, etc. Right, I keep turning it, and after I touch all the wheels, so you have infinitely many of them, the handle disappears, right? So nobody is turning the handle anymore. So it's kind of a sitting at the infinity. But the system still produces heat, right? There is still friction, it's still moving, it's producing heat. So this is something what we call the backwards energy cascade. It's observed in physical, it's observed in fluids, experimentally, numerically, in 2 dimensions especially, but on low modes. Nowadays, thanks to Camille and Lazar, we can do it on high modes, right? And we call it convex integration. Right, so again, now we have some kind of pathological mechanical system, right, where the energy is always transferring from the right, and because there are infinitely many elements in the system, the total work is 0. There is no work, there is no force, but the system is dissipating the energy.
What
Anyway,
if you try to attach a wheel to a second wheel, like to the side?
Second one?
Yeah, or third, like basically not like in a chain, but try to attach another one to the side that you have one wheel not attached to 2, but to 3.
Well, yes, of course, you can make it more complicated, right? The whole point is that if you have infinitely many elements, the conservation of energy does not have to hold anymore. That was the only point, right?
I mean, you're kind of thinking of the wheel as the scale of the forcing that you're putting.
Yes, that's your force. That's your force. So now it's basically sitting at infinity. So it's you have, I don't know, you have some little creature there, right? Turning the wheel. I was trying to draw a picture of Maxwell's devil, who knows how to open a small door for slow molecules, right? So here he has to do a different job. Here he has to basically inject energy at 0 scale. We don't see it, right? We don't see it, but because of this, the energy conservation does not hold anymore.
I have a question or two. In the first case, you're looking at non-Leray-Hopf, and yes, you can have a singularity. That's what this dash means. The second case is Leray-Hopf. Do you also have a singularity? You're drawing a...
Yes, H1 norm blows up. So it blows up, right? And then what happens after that? I have no idea. You can have, H1 norm can become finite right away, or I mean, it's, or you can have.
It blows up and then the H1 norm becomes finite. Is that what you're saying?
No, I say that there can be several possibilities. We don't know. We don't know because nobody ever constructed an example of a blow up.
Okay.
Leray-Hopf solution. Right? But in principle, if you look at exactly the time of blow-up capital T, in principle, the H1 norm can become finite, or you can have a blow-up from the right.
Right, it can go either way. That's what you're saying.
Yeah, it can be either way.
Now, in the convex integration, you're not saying the total energy is infinite because you start with a finite amount of energy and you decrease it. So what is the issue here?
Well, so we can easily arrange it so that the total energy is finite. The issue is to have a mechanical system, right? There is no force, but it's producing energy.
I
And
understand.
it's equilibrium, right? So it's not.
Okay, so the total energy is finite. So what is the point of the example? If something is going off to infinity, but what? Speed of the wheels?
No, the wheels are turning with constant speed. Everything is constant here. It's equilibrium, it's a steady state. And it's producing heat. But there is no force. The work done by the force is zero, but it's producing heat.
Okay, so it should just dissipate all the energy in some amount of time, which might take forever.
But the wheels are rotating with constant speed. They're not slowing down. The kinetic energy stays the same. The kinetic energy is not changing.
Okay, so is this related to the idea that the energy is being transferred in a real fluid to smaller and smaller scales?
Yes, exactly. Right. But for the second example, I reverse the direction. So now the energy it's transforming from small scales to large scales. Right. And that's how you get this pathological.
Now it's clear. Now it's clear. Thank you.
Okay. Okay, I have to speed up a little bit. Okay, so now let's do a bit more serious computations. And here I'll go very fast. So again, we want to look at the dynamics, and I'll start with the simplest model. Let's just look at the kinetic energy, which is 1/2 of the L2 norm squared and the entropy. So let's just see what happens to these two quantities. So this is the L2 norm of the grad U. So we already learned that, at least for smooth solutions, the rate of change of the energy is minus nu times. Okay, now, natural question is what happens to the rate of change of the entropy. And here I'll just write it down. You probably have, many of you have seen this, of course. Check the dimension. If the dimension is correct, or if the units are correct, and the estimate should be correct. Plus C over nu cubed to the power 3. So what I did here, I applied, I erased Navier-Stokes, but anyway, Holder and Sobolev for Navier-Stokes, I used Young, I used 1/2 of the linear term to kill a part of the non-linear term, and then some interpolation for the linear term. Anyway, it's a simple exercise. Now the question is, what if we look at the worst case scenario, replace the inequality here with equality? So we have two equations, two unknowns. We should be able to draw a phase portrait. Going to the entropy versus the energy. Again, so one thing I have to do, I have to erase this 2 here, otherwise it's not a good model. I'll let you think of why. Then the energy can become negative. I don't want that. So anyway, how do we draw a phase portrait? It's non-linear, right? A good way to analyze it is to look at a scaling invariant quantity. E times k scaling invariant, it scales like H1/2 norm or 3 norm. You take derivatives. Product rule E prime k plus k E prime is going to give us, I'm going to factor E squared. Right, so from the first equation, I get minus nu E squared. From the second one, you get minus nu E squared, so minus 2 nu E squared. mu a squared. And then the last term plus c over nu cubed times k times e. Okay. So now we found one solution, right? If oops is squared, I said it's no squared. Okay. Right? Okay, good. We found a solution. So if initially k times e is chosen so that you have 0 here, then it's going to stay that way, right? So we have a solution, we have a trajectory, looks like this. Along this trajectory, k times e is some constant times nu to the power 4. If you start somewhere in this region, again, your solution is going to blow up. It's easy to check that these solutions blow up in finite time. You just look at the second equation. E is going to blow up in finite time. It's obvious. So you start anywhere here, it's going to blow up in finite time. If you start in this region, all the solutions go to the origin. So that's something what we call a small initial data result. So if initially a norm which is critical with respect to the natural scaling is small, then nothing bad happens. There is no blow up. And by the way, this solution, what it does, it actually loses all its energy when it blows up. This solution has been excluded by Vladimir and collaborators. So this is the famous Asperger-Serrin result. And that if a critical norm like H1/2 or L3 is bounded, the solution is regular. As you can see, you cannot get it using energy methods. So in this functional class, there is no smallness on high modes. The nonlinear term in principle can dominate the linear term. Okay. So now a natural question is, well, what we did, we replaced the inequality with equality. So what if what if the estimates that we did here are not sharp? So for example, U is divergence free. Here I didn't use the fact that U is divergence free. So what if it helps us? What if there are cancellations? Well, there are no cancellations. We can actually construct, I can write down, well, I probably won't have time to write them down for you, but there are divergence-free vector fields that saturate this system. Let's call it KT, and you can arrange them. So let's now draw a picture in H1, maybe H1. That's going to be our phase space. So now basically what I want to do, I want to take this simple dynamics and embed it in the real equations. I listen to too many geometry talks. Anyway, so that's going to be the origin. So we can construct a, let's call it a path. A path of divergence-free vector fields where this model holds. And if you'd like, you can even take a small epsilon neighborhood of this path. Okay, the model is going to hold there, maybe up to some constant. If a solution decides to stay there, it's going to go up. Okay. So what's the next thing you want to do? The model was way too simple, right? We only looked at the energy and entropy, right? In general, you want to see how the energy moves to smaller and smaller scales. So let's do the following. So let's take this road to blow up, and let's try to analyze what kind of dynamical system you have inside here, right? And let's see how the energy moves to smaller and smaller scales. So I'm going to call AM. That's going to be the L2 norm of U projected onto modes around some frequency 2 to the power n. Okay, so well, it doesn't matter. You can take a sharp projection or Littlewood-Pelly projection, so convolution with some bump function phi, right, still bump function. And then the natural question is what happens to the energy in each dyadic shell. And in this region, you'll see something like this. You'll see the following system. An prime is minus, so this is a linear term, that's easy, it's always the same. Nu times the frequency, I call it 2 to the power n, an, and then the interactions in the nonlinear term. So some energy will come from the previous, from the larger wheel, right? From the previous wave number. So that's going to come as plus 2. I can explain where the power comes from 1. So 1, that's just the derivative, and then you have to go from L infinity to L2. You have to use Bernstein and Sobolev. So it's going to be d over 2. N minus 1, n minus 1 squared. So that's the energy coming from the previous wheel, and then some is going to be transferring to the next one. So minus 2 1 plus d over 2 times n plus 1. So this is something which is called the dyadic model. So now we have an infinite system. And 1, 2, several infinite system of ODs. Right. Thank you.
So this is the Bernstein inequalities, right?
Yes, very good. Yeah, so I don't have to explain where this comes from, right? Again, so yeah. So remember, in this region, yeah, basically, so this is a regime where the Bernstein inequalities are saturated, right? That's when the flux is as large as it potentially can be. So that's where d over 2 comes from. Okay, so this is something which is called the dyadic model. Was originally introduced by Desnyansky and Novikov. In 74, then it was reintroduced by Katz and Pavlovich. And the natural question is, do solutions of this model blow up? So now you have a much more detailed toy model. And they do blow up. When the dimension d is strictly larger than 4. By the way, for the model, d does not have to be a natural number, it can be a real number. So when it's strictly larger than 4, I'll blow up. Well, when it's less than 2 or equal to 2, regularity just using energy methods.
Just one question. You're saying that if you're in this class that saturates the inequality, that the dynamics of Navier-Stokes sort of decouples or becomes local in frequency somehow?
Well, yeah. So basically, that's so I started with a very specific path, right? That's so the way I constructed it. I wanted everything to be saturated. I wanted the flux to be saturated, right? So it's not like it happens everywhere. It happens along that very specific path.
Okay.
And the question is what the solutions actually want to stay there, right? So anyway,
But this is not strictly true. It's just a model.
Well, okay, so it is a model, but in that path, it is true. So if you look at that path, you'll see that indeed everything is local. That's how you maximize the flux. You want the energy to be just in 2 consecutive dyadic shells. That's how you maximize it.
I mean, what you don't know is that the solution will stay on that strike.
Yes.
And actually end up.
Right.
Like it not simply escape the boundaries.
Exactly.
But if it stays in that cylinder, then it's going
Right.
So that's the assumption you make.
Well, yes, right. That's something you're making when you're deriving the model, basically. You're just basically looking at what happens point-wise in that region, right? What happens, everything is local in Fourier space. And then you look at the flux of the energy and you derive the one. Okay, so let me continue. So, well, when the dimension, I don't know whether, so I have to stay with this. When the dimension is 5, one can say, okay, well, can you take a below solution of that model, so it's already a more precise model, and try to somehow embed it in the real equation, and you can do something like that. So maybe I'll write it down very, very fast. You can basically again find the path that comes now from the more precise model. And then you can define a projection. So either sharp projection or a little bit Pelly type of projection on all the modes visited by that path. And now we can modify the bilinear form. So the bilinear form BU is just the Leray projection to the divergence free vector fields U dot gravity. Now if you modify it in the following way, it's similar to what Tao did. I'll explain his results as well. If you modify it in the following way, so just take some, so I can design a projection in Fourier space, and then we project B and project each. Then equation dt u plus d tilde u is a new Laplacian. U admits solutions that blow up. So there are solutions.
These are projections on some shell or into less than or equal to?
Some, yes, not shells, really, not shells. These are more complicated, but these are really projections on some Fourier modes. So I basically specify some Fourier modes, right? And I project the bilinear operator to those modes. So basically, I turn off some interactions. I turn off many interactions, right? But I still leave some, and then solutions blow up. Okay, so now let's go back to the.
I still don't understand what you're projecting onto it. So
Well, that's the thing. I cannot tell you. I cannot tell you. It's a complicated, but it's a projection operator.
Okay.
But it's a complicated one, right? So basically, I have to.
Is it time independent?
Oh, it's time independent. So I have to take basically a solution that I obtain from here. So I start with some path again, and then I take all the Fourier modes ever visited by that path, and then I project on those Fourier modes. Anyway, it's a complicated.
I mean, it's like some invariant set of lattice points, right?
Well, yes. So it's anyway. It's some projection operator. That's all. Okay. So now the question is, what happens in? Let's go back. What happens in three-dimensional case? All right. So it seems. I mean, we have now. Let's try to go back to the regularity problem. All right. So we have a big gap between 4 and 2. So how would one attempt to prove regularity? Right. So clearly we have an obstacle, right? If your solution decides to stay here, it's going to blow up. So energy methods are not going to work. So one way to attempt to prevent the solution from blowing up is to design some kind of roadblock. Find some invariant set. Right, if you have a positive invariant set. So what if we can design a positive invariant set? So basically, solutions that start inside, they cannot leave the set, they have to stay inside. So it's called capital X. So it has to have, well, it doesn't have to, but if it has the following properties, so X is positively invariant. If you want to prevent blow-ups, then it's better to be bounded in some subcritical space. H what is it? D over 2 minus 1 plus, so some subcritical space. And also we want the origin to be in the interior. So you want some like a small ball to be contained in X. some small block of resistance. Okay, that's going to prevent blow up from happening, right? Solutions which stay inside, I mean, we start inside are going to stay inside. If you have a solution which is blowing up, but it starts somewhere else, you can just do a simple rescaling. That's why I put plus here. This is not a critical norm. It's going to be changing rescaling, so you can bring the initial data inside of this small ball, and that's going to give you a contradiction. So no blow up. And this was actually done.
So where are you using?
One second.
This was not, because this,
Well, not for Navier-Stokes, otherwise.
that's what
It was done for the dyadic.
for the dyadic.
It was done for the dyadic mode, right? It was done for the dyadic mode by Barbaton. I'm writing. 2011. They proved that when D is less than or equal to 3 plus some maybe tiny epsilon, then there is no block regularity. Oh, so what remains to be done is to find an invariant set for the real equation.
Oh, wait a minute.
Anyway,
You're saying
but it was highly non-trivial. It was highly non-trivial construction, so the set has to be very, very special.
I'm confused. You're not saying that something in D = 3 stays regular for any data. You have to have something.
Right. This is all for the dyadic one. All the results, I'll be one more.
Okay.
It is for any initial data, right? For the dyadic model. Yeah.
Okay, so it looks like it's a good news for the Navier-Stokes equations. Well, then Tau came along. And what he did, he added a delay mechanism to the dyadic model. Dyadic model plus some delay mechanism. I mean, it would take the whole blackboard to write down the system equation. Okay, I'll just try to explain the idea. For the regular dyadic model, how the blow up occurs for the regular dyadic model. So this is going to be AN versus, So you start with something smooth, so the coefficients decay very, very, very fast. And then they want to become on Sagar regular. So they start decaying as a parallel. So that's how blow up occurs for the dyadic model. So what Tau did, he introduced delay mechanism so that the energy flux is always local. So AN look like this. Right, they're always localized and they're just moving to higher and higher modes. Well, not even moving. This is a wrong word. It's nothing like sort of similar. It's they're basically replicating themselves. They're constructing a copy of themselves on higher modes, and that's how you produce the most optimal flux, energy flux. And again, he designed some operator B tilde. So in his case, it's a bit more complicated. So he has to use some dilations and some rotations, but one can actually design a bilinear operator so that solutions of that modified Navier-Stokes.
So are you saying that Tau's results can be recast as a convex integration result?
No.
They're just a matter of looking at the right projection operators.
Right. No, yeah.
Okay.
So I didn't get to convex integration yet. I was planning to. And I'll still have time to say a couple of words. Okay, so now let me go back to this path to blow up, and I mean let me try to explain how vector fields look here. How do you maximize the flux, and what kind of results can you obtain? Okay. To maximize the flux, if you just think about the nonlinear term in Fourier space, you want to maximize the number of interactions. Right. So think about having two Dirichlet kernels interacting with each other. Okay, and producing something like higher frequency. Okay, so then the energy is going to be transferring to higher and higher modes this way. In physical space, what does it mean? You want to look at vector fields which are concentrated, or I like to call them intermittent. So Dirichlet kernel, that's how it looks. So this is the length scale L. So we say that corresponds to the intermittency dimension 0. So think about having one AD at each scale. And what's special about it, it saturates Bernstein inequality. So if you compare the L infinity norm and the L2 norm, then you have L to the power. So I'm in 3 dimensions now, 3D.
Alexey, you wrote L2 twice.
Oh, okay. Yeah, one should be L infinity. D over 2. Or rather minus D over 2. Okay. So which vector fields do not do a good job? Take sign. Okay, so these are. So this is the length scale L. Corresponds to the intermittency equal to 3. So ADs occupy the whole space. What we call, this is something what we call Kolmogorov 41 regime. So in this case, the norms are going to be comparable. Anyway, so using such vector fields, I can come up with various constructions. I'll just a few of them. And so with Roman Shvetko in 9-10, we constructed discontinuous solutions, Leray-Hopf solutions. Not just weak solutions, Leray-Hopf solutions in the largest critical space, d minus 1, infinity, infinity. I'm not going to define it. It's a space that contains all the scaling invariant spaces. And also,
so this is a Besov space, right?
yes, it's a Besov space. It's a Besov space. Sorry, there is no way. Well, yeah, there's no way I can
It's all
define
right.
it.
I know what it is.
Good. And so this is the second result. If actually U is continuous in this space, you can use it. So again, the construction was done using this type of, vector fields where the flux is maximized. Then recently with Mimi, wrote it down just very recently, but we had it for a while. We constructed discontinuous solutions. Again, Leray-Hopf solutions. In B0 to infinity. Again, it's a Besov space, but it scales like L2. So it's kind of right on the borderline of L2. But it's a Leray-Hopf. It's a Leray-Hopf solution.
Now, wait a second. So Leray-Hopf has epochs of regularity, though.
So yes. So it means the discontinuity is at the origin.
Okay.
Of course, right. Otherwise, we would have to prove the millennium problem.
Exactly. So that's my point. Yes.
Okay, and another result is shout out. So it was something very. Oh, did I read it? I read it. I read my picture. So remember, so we had a road to a blow up. Right, and so in the first result, basically, we pushed everything to the origin, right? So it's easy to control the structure, I mean, if you have to do it only instantaneously. Okay, with shear tau, we used the force to control the structure. So the force was more or less, it was orthogonal to U, and it was on the borderline of Leray-Hopf class. So if the solution tries to leave that region, you kind of kick it back in, and then it has to blow up. So it was kind of, it was optimal on Sagar blow up, but for a force which was almost Leray-Hopf.
So the force is still singular?
So singular at the time of blow up. So until the blow up, everything is smooth.
What do you mean by a forcing being Leray-Hopf?
So it's not L2H1, but it's right on the borderline of L2H1.
I see, okay, fine.
But again, everything is smooth up to the time of blow up.
So this is.
Anyway,
You write that down, L2H1?
This is an extra force term
Sorry, go
in
ahead.
the equation. Oh, wait, I'm sorry.
Sorry, I didn't hear.
I think two of us were talking at once. Just
Right.
go on. I'm sorry.
So the force is almost Leray-Hopf. It's smooth, but it blows up. I mean, but it's all. Anyway, L2H1. I don't remember where. We can put minus anywhere, somewhere. It doesn't matter where minus is. But it's in a sense we can make it orthogonal. Yeah. We can make it even so that it leaves kind of, it supports this disjoint from U in the Fourier space. But anyway, so it does not help you to blow up. It just,
Well,
it keeps it inside the
Orthogonal, you mean in the
acting
L2
like
sense?
this.
Orthogonal, you mean in the L2 sense?
Okay.
L2 sense.
This is a bit harder to explain. It does not produce any anomalous work. And I would have to define what it means. Right? Because once you are, if you are not in the Leray-Hopf class, then,
But how does it relate? I mean, how does it relate to like Scheffer's example?
Oh, but so that's in physical space, right? So it's kind of disjoint from you in physical space. In our case, it's kind of disjoint from you in Fourier space.
Okay.
Yeah, so it's very different.
So would you be able to translate Scheffer into yours?
Oh, that's a good question. I have no idea. So that's a good question.
Because it's in a sense, it's like
right.
decreasing the energy inequality. So
Right.
it's certainly not producing, I mean, it's producing work, but it's producing work like, in the opposite direction. So
Right.
if it's producing work, it's actually dissipating more.
Yeah. No, I mean, that's a good question. I haven't tried. Oh my God, I have 6 minutes to talk about convex integration. I did something bad. Okay, so in all these examples that I showed you, so we try to, there was another example where we try to construct well solution of Euler, but I'm not going to write down the space we obtained, but the exponent was sharp, it was 1/3. But anyway, in all those examples, we try to produce optimal flux, right? Building vector fields so that the energy moves from one shell to the next shell. Okay. What Camilo and Lato taught us, maybe we shouldn't be so greedy, right? What is the idea of convex integration? You have a Reynolds stress, so that's your error that you want to kill, right? By constructing something on higher modes. So let's say U now satisfies the Navier-Stokes equation. This is some error. The divergence of some stress R. And the goal is to construct a perturbation. So replace U with U plus W so that the Reynolds stress becomes smaller in L1. So we want to reduce the L1 norm of the Reynolds stress. And again, what if you don't try to build something around Reynolds stress, in the next dyadic shell? What if you zoom out? Zoom out, you'll see a dot, right? A constant. So this is Fourier space. Everything is in Fourier space. We see a constant. How do you kill a constant? Just take a cosine. So this is going to be a direction. We'll have to do it for some set of directions. With a large wave number, lambda, take cosine lambda x, and that's going to be the building block W. So what happens to W tensor W? So I'm just writing everything in one-dimensional case. It's cosine squared. So I multiply it by 2, I guess, right? I get exactly 1 minus cosine y squared. So something moves to higher frequency, but also you reduce a constant. And now what you want to do, you want to just multiply both sides by r, and you are done, right? You kill your Reynolds stress. Now you can design a perturbation, little double, which is the square root of 2r capital. It's going to do the job, right? Of course, one has to worry about what happens on high modes, and that's a big difference between Euler and Navier-Stokes, because for Euler, to take divergence, this term is going to disappear for basically, for simple flows like this. For Navier-Stokes, the intermittency has to be high enough. I didn't mention this, but I should have put it as one. Yeah. So when the intermittency is, it's a theorem. When intermittency is larger than one, we need some kind of Dirichlet kernels, right? And then you have non-diagonal interactions. You have to deal with this bad term and Tristan and Vlad managed to handle them and proved that indeed there are non-unique solutions for the Navier-Stokes. In L infinity, H0 plus some tiny epsilon. And recently is Xiaotao constructed non-unique solution. So we use temporal intermittency. Well, if I have 1 minute, I'll tell you what temporal intermittency is to construct non-unique solutions. On the borderline of Prodi-Serrin classes that I probably erased a long time ago. So the first one is L2 on the borderline. So L2 minus in time, L infinity in space. In all the dimensions, so these can be 2 or larger. And in 2D, do it in C L minus. And 1 minute to tell you what temporal intermittency is. I do. Okay, good. Remember that picture of a picture on 0 scale, rotating a wheel. What if the creature learns how to cheat the time, and then learns how to rotate the wheel infinitely fast on time intervals of length 0? Then, so usually, I mean, so for the example that I gave you, the flux, the energy flux was something like this, right? That was the flux of the energy. This is M. So the first wheel, second wheel, etc. This is the energy flux. What if you reduce it in the following way? Okay, so it moves to the left. Right here it moves faster, and then here it moves even faster. So that's what we call temporal intermittency. So let me be a bit more precise. So you take a Reynolds invariant stress, and you decompose it in the following way. You multiply by some function d squared plus 1 minus d squared. Very simple. Where g is your favorite intermittent function in time, we just pick an intermittent function in time. Okay, so it's going to be 0 most of the time, and then it's going to be right.
So there's no question about how it's the peaks scale with the frequency of the peaks, or that looks.
Well, yes, of course.
That
Of course.
looks-
There are many parameters that you have to play with, right? And then that's how you can basically separate. You can separate the scales. You can separate the fast time variable is from the slow time. And then what you want to make sure you want to choose g so that integral of g squared is 1, so that this term is of 0 mean, and then you can easily control it. You can kill it by a temporal vector. Right. So in a sense, what you are doing, again, I've into too many geometry problems, but let's say you have some kind of path, right? And then you have a vector field, right, given by your equation, so it forces you to go in some direction, right? But on the other hand, you want to stay near the path. And of course, for the Navier-Stokes, there is no ampleness. I don't know if I'm using this term in the right way, but for the Reynolds Navier-Stokes, there is. So you can easily pick a different direction. So what you do, you say, okay, well, let me just follow Navier-Stokes, right? And then at some point, I'm going to turn and come back to the other side of the path. Right, that's when we actually do convex integration. And then again, just follow Navier-Stokes. And at some point, you just decide to come back to the other side of the path. So again, that's when you do convex integration. Well, I'm out of time, I'll stop here.
Just
So I didn't understand what's the result you get from this construction?
Well, this too. So it's just, I try to explain again for time how one can implement temporal intermittency into a convex integration scheme. Basically, the idea is to only do convex integration on very, very short time intervals, but then you kind of have to overdo it, right? And then you let pretty much the equation do the job.
And you get singularities in time.
What do you mean singular? Well, yes. So in time, yes. So in time, you're of course. I mean, you don't get infinity in time anymore. It's
I mean,
yeah. So in time, it's not going to look nice in time.
but somehow you're building in these intermittent things that.
Right. Yeah. So in time, you'll have basically blow-ups non-stop everywhere.
but does it look like does it look bad only in some sparse?
Yes. Yeah, well, yes. Right.
It's smooth on lots of.
Right. Yes, it's smooth in a huge set. One can say, oh, I don't remember the dimension. How's the dimension here? I think it's like 1/8 or something, right? Of the bed set.
So the creature is really doing really on a tiny set.
So you're bringing stuff back from infinity on this tiny set to kill things out, to well prepare your initial data to run well over the next chunk.
Yeah, it's pretty much.
And then you bring back from infinity to kill on a chunk.
Yeah, exactly. Yeah.
Do I understand correctly that the dyadic module is still open in 4? E equal 4?
Yeah, well, between 4 and 3. Yeah, yes, including 4, yes. But the whole interval between 4 and 3 is still open.
But there are many shell models, right? I mean, I've seen many shell models, whole books on shell models. I don't know.
Yes, so there are Sabra shell models, but those more complicated shell models, well, they're simpler than Navier-Stokes, but
It's still same problem.
But exactly, so there is, I haven't seen a single result that cannot be done for Navier-Stokes, but can be done for Sabra. So it's still just, I mean, they're basically, their dynamics is too complicated. So we cannot do anything. So it's basically, instead we can study Navier-Stokes.
So this is one of the simpler shell models.
Yes.
So other shell models that you're saying are even more difficult.
Right, they're as difficult as the Navier-Stokes itself.
But in terms of scaling, they're simpler, right? So in terms of scaling, they're like d = 2.
Oh, no, of course, you can play with scaling, of course, if it becomes
Sabra
critical.
and Goy are, I mean, so the way you explained it is that the intermittency is built into the shell model,
Yeah.
the parameter D.
Yeah,
But in Sabra and Goy, D is equal to 2. So that would correspond to no intermittency. So what, I mean, I was trying to ask, somehow physicists work with those models where in terms of scaling of the model, there's no intermittency, but they're searching for physical intermittency with those models.
I mean, the intermittency is not built in, but it's there. I mean, is it there?
It's coming from the dynamics.
I
It's not
think
built into the model.
I think they're looking for temporal intermittency. Right. So yeah, so the spatial intermittency is kind of built in, right? But if you look at the dynamics, right? So I think they're looking for temporal intermittency. So they're looking for spikes in the, in the energy, basically, right? That's my understanding. But I never worked with those models. So.
Vladimir wanted to ask.
Actually, how is it with Katz-Pavlovich, but if you don't assume that the solution is positive? If you allow the side.
Oh, then basically it becomes Obuchov model. So it's the same as, so basically then you have backwards energy cascade, not forward energy cascade. Then you can start proving results like non-uniqueness, but on the other hand, you don't have blow up. You just reverse the cascade of it. You can just,
But so in general, can you prove blow up or regularity if you don't have any?
I'm sure they're regular, but solutions are non-unique. And there are some results in that direction. I don't remember exactly, but
okay.
That's, for sure regular, because there is no forward energy cascade. That should be regular. Right? If you start with regular initial data, it should be the solution is regular. But because of the backwards energy cascade, you have non-uniqueness. For the dyadic model, you have uniqueness.
So just to kind of follow up on Tom's question. So in that particular shell model, you talked about 2 decades of perspective. What is the most important thing about that makes it solvable? Is it that it's positivity preserving? So what's the feature of that that's most important?
It's a good question. It's the flux. You have a low bound on the flux. So the flux.
But is that because of the positivity?
Yes.
The size of things?
So the nonlinear term is the one that makes the solution more regular, basically. So it regularizes the solution by pushing the energy forward by spreading it in free space. So it's like for burgers, right? It's like for burgers, when the shock occurs, right? It's like a power law, right? So, you can see it in kind of in physical space, right? Of course, you have maximum principle. Right, so it gives you control on infinity node. But for the dyadic model, of course, there is no maximum principle unless you do Fourier transform and you have something non-local and you can still anyway. But yeah, so it's everything is in Fourier space. But still, you can kind of see that the nonlinear term pushes energy forward. That's why Tau had to introduce a delay mechanism to make it to make solutions more so to make a blow up possible even for
Make the dissipation of energy less efficient.
Right, exactly. So the most efficient flux is when all the energy is staying basically in 2 consecutive shell models. Right. Once it starts spreading, you lose. It's a bad news for blow up, good news for regularity.
To go back to the earlier stage, is there any intuition for how you choose these projection operators that give you these bilinear forms?
In which case? In case of the dyadic model or in case of Tau's model? For Tau's model, it's really complicated.
No, let's go to just the dyadic model. That should be easy.
The dyadic model, basically, it's still so. Again, so it's still a bit complicated. So if you start with the solution of the dyadic model that blows up, and then you look at what actually happens in the phase space H1 for those vector fields that I tried to describe, right? That,
right.
Saturate the flux. So you can construct some kind of function, right, v of t in that vector field, it's not going to be a solution of Navier-Stokes. But what you can do, you can say, okay, what if I am going to restrict all the other interactions, right? What if I'm going to project on the so I take the union in time of the support of the Fourier transform of K. Of the rate. So basically project on all the Fourier modes ever visited by that function. So that's how I define the projection.
That's
You turn
helpful.
off all the other interactions.
That is helpful. Thank you.
Okay, I guess we got plenty of questions. So I invite everybody to ask more questions at the T.